two objects, X and Y, which were attached by a string, and the center of mass is depicted here. And we are told that the distance between the centers of masses is 2 meters, and the length of the ramp is 7 meters. We have an initial velocity of 0. It's released from rest, so it's going to accelerate down the graph. How much time will it take the center of mass of object X? So the center of mass of object X is this. So we want to know how long will it take this green line to reach J. And what we can see is that is 9 meters. Now we would normally expect this to behave according to this equation, x equals 1/2 at squared plus v0t plus x0. And if we say the initial position is 0 and the final position is 9, that drops out. The initial velocity is 0, so that drops out. And we want to know how long it will take to get to 9 meters. So we have two unknowns, the acceleration and the time. And what we are told in this graph is that we have the velocity versus time. Now, the information we can get from a velocity time graph are the things we can read, which are always the axes, velocity and time. The slope is given as delta v over delta t, and that is the definition of acceleration. And the area is v delta t, which is delta x. So on the one hand, we could be looking for the area to be 9. That's one way to address this and solve this. Another way might be to determine the acceleration and plug it into our equation above. I'll start with doing the equation, then we'll go back and consider the area. So the acceleration is the slope, and so the coordinates of this point are 4, 8, and 0, 0. So the acceleration, delta v over delta t, is 8 minus 0 over 4 minus 0, which is 2 meters per second squared. So if we plug that into our equation, 9 equals 1/2 times 2 times t squared, we'll find that t squared equals 9, and therefore t equals 3 seconds. So if we look at the choices, our answer choices, we can see that we have 2.7, 2.8, and 3.0. So 3.0 is one of our choices, and this may be the most expedient way to do it. We could also, however, start figuring out the area. And we could compute the area of this first little trapezoid, or excuse me, the first little triangle. And so we've got 1 times 0.5, so we have an area of 0.5. We could do the area of the next. And what we can see is that all of these little triangles are going to be 0.5. And so this has an area of 0.5 and 1. Excuse me, I did that, labeled that backward. The area of those little triangles is not 0.5, it's 0.25. We have 0.5 times 1, which would be the whole thing, and half of that is 0.25. So all of these will be 0.25. And the area of each one of these little squares will be 0.5 times 1, or 0.5. So 0.5, 0.5, 0.5, 0.5, 0.5. And so if we start totaling these up, we get 0.25 for this column. We get 0.75 here. We get 1.25 here. We get 1.75. We get 2.25. 2.75. And that each one of these is for that total column. So the cumulative area we get by the time we get to, say, 2.7 seconds, which would be about here, we add these two up and we get 1.0. And by the time we get to here, we get 2.25. And here we get 4.0, 2.25 plus 1.75. 4.0 plus 2.25 is 6.25. And then we've got this small area, and if we added the entire all the way up to 3, well, we'd have 6.25 plus 2.75, which would be 9.0. So we can see it will take us all the way to 3. Yet another way we could do it utilizing the area would be to try out the different answers. We could go to 2.7, read off the values, and calculate the area that's under 2.7. 2.8, we could do the same thing. 3.0, we could do the same thing. And 3.5, we could do the same thing by process of elimination. The problem we run into when we do that is that there is uncertainty associated with reading the values off for 2.7 and 2.8. And the uncertainties are sufficiently large that it could cause you to choose the incorrect one. So after looking at all those different methods, it seems like the easiest way to do this is to use the equation, obtaining the slope from the graph. And that's why it's 3.0 seconds.